Okay, welcome everybody to Integrity Journal Club. And today I'm very glad to introduce Congkao Wen from Queen Mary University, London, who will tell us about integrated 4-point correlators in unequal form superunities. Please, Congkao.
Thank you. So first of all, thank you guys for inviting me. And I guess you will see that I'm not going to talk about anything about the integrability. But anyway, so I will talk about integrate 4-point correlation functions in enforceable YAMLs. So the talk is mainly based on this paper. We also summarized some of the main results in this short one. This work is done with collaboration with Daniel Doligoni from Durham and Michael Green from Cambridge and the Queen Mary. All right, so the main, say, physical observable we will study in this talk are the correlation functions in enforceable YAMLs. And I think it's fair to say that they have been a subject of interest for about 2 decades, especially since the discovery of ADS-LT duality, which says that a quantum gravity in a ADS space is dual or equivalent to a conformal field theory on the boundary. And the physical observables, such as the scattering amplitudes in ADS space, is equivalent to correlation function in the dual CLT. So a canonical example of ADS-LT duality, which we will study today, where on one side we have type 2B superstring theory on the background of ADS5 plus S5, which is dual to a 4-dimensional conformal field theory called enforceable YAMLs. So this is a maximal supersymmetric YAML theory. And then the alpha pi expansion or low energy expansion of the string amplitudes now is mapped, according to ADS-LT duality, is mapped to large N expansion of the correlation function in type 2, in enforceable YAMLs. Then the coupling, the string coupling, so I call tau S. As you know, that in string theory, the coupling is given by expectation value of the scalars. So in this case, the axion and dilaton. I emphasize here, as will be clear, that we really want to study the complexified scaling, coupling, because we want to study the non-perturbative effect. So we will keep it both. And that will be identified with the YAMLs coupling. Again, it's a complexified coupling, which contains both theta angle, often you ignore, and the YAMLs coupling. Well, the reason we want to really keep both of them, because type 2B string theory as well as enforceable YAMLs famously enjoys the so-called modular symmetry or SL2Z symmetry, which takes the coupling, the complexified coupling, to a new one where A, B, C, D are the integers, and AD minus BC equal to 1, so namely SL2Z. So here I'm making explicit what the complexified coupling is. So in the field theory, so this is a theta angle plus I divided by G YAML square, where in string theory, this is the expectation value of the axion, and this guy is related to the expectation value of dilaton. Sometimes I will also use the tau 1, so refers to the angle, and the tau 2 is related to the one of the coupling square. Okay. This duality is sometimes called the S duality, and in field theory it's called the Montono-Oliver duality. Right. So as I said, we really want to study this SL2Z duality, and to do that, from this transformation, it's obvious that the duality relates the theory with weak coupling and the strong coupling. So to study such a duality, we really have to compute the amplitude or correlation function at the finite coupling. In general, computing anything at finite coupling is hard But luckily in this case, so in the case of string theory, at least in flat space, due to the work by Green and his collaborators, this was known quite a while now that at least for the first field order in the low energy expansion or in the alpha pi expansion, the string amplitudes are known to all order in string coupling. I will review briefly at some point when it's necessary. So, well, as my title shows, so our goal is to study the correlator. And we will try to study the correlator for arbitrary n. So m is the rank of the gauge group, and for arbitrary coupling. Sounds a bit too ambitious, and we will see. And in the larger n expansion, as I said, you know, the EDSLT duality tells me that this will be related to the alpha pi expansion of the string amplitude. And as I will show, that indeed the result will obtain from the correlator in the larger n expansion. Furthermore, you take a flat space limit, will reproduce the known results due to Green and his collaborators. So from ADS-CLT point of view, so this is a kind of precision study of ADS-CLT duality, since we go beyond supergravity and beyond the perturbation. In particular, say the Yamil-Sinstone effect is going to map to the D-Sinstone effect in string theory.
Congkao, sorry,
yes.
So you have your microphone is probably touching something because.
Oh, sorry, you found some noise.
Yeah. Yeah, it's better.
Okay, let me try again. Is it better or?
Yeah, it's better now.
Okay. So let me know if it's still noisy.
It's worse again.
I see. Should I just take it off? Maybe it's better. Let's see. Can you hear me?
Yeah, perfect.
Okay. Okay. All right. So here's the outline. I will review some general property of the 4-point correlation function we were studying. So this is the 4-point correlation function of the superconformal primary operator. Very brief review. Then I will introduce this quantity, so-called integrate 4-point correlators, and especially to emphasize how they can be computed from supersymmetrical localization. Then mostly I will focus on well, there are basically three, but I will focus on two, and at the end of the day, I will focus on only one. So mostly I will focus on one of the integrated correlator, and we will present a exact formula for such integrated correlator for any n and any coupling. So this is a conjecture. We were not able to prove it at the least. So I will derive this formula for the simplest case, SO2. Then I will make a conjecture. For the rest of the talk, I will basically study this conjecture, the formula. Say I will do a small coupling expansion for arbitrary n. So this will basically is a loop expansion. Then I will study say larger n expansion, both for small lambda, namely the Halter expansion, or large lambda, especially to study how the theory is convergent, how you can do resurgent if it's not convergent. And the last part will be about larger n expansion, as I'm emphasizing, at the finite coupling and the finite theta angle. And this part will try to make a contact with, say, string amplitudes on ADS5 cos S5. Then you can take a flat space limit to compare with the known answer due to Green and the collaborators. So finally,
could I ask? So I mean, probably you obviously will explain, but so you are going to consider localization of, I don't know, deformation n equal to star, say, and then expand in the deformation parameter.
That's correct.
Rigorously derived localization formula. Why is it a conjecture then? Are there some subtlety?
Oh, you have derived this formula from localization, because localization gives you like an n-dimensional integral, right? If you.
Yeah, so then you simplify it further.
We will of course, n-dimensional integral for any n in some sense not that useful. Well, it's of course better than partial integral clearly, but it's still n-dimensional integral for n. So we will present like one-dimensional integral.
So it reduces to one-dimensional for n. Okay.
Right. And I think more importantly, to make it manifest the SL to the invariance. All right, so I will conclude then make say comments about the future directions. Right, so which correlator we will study? We will study the correlator of the following superconformal primary operator. So as you know, N4 has 6 scalars. So I denoting the SO6 asymmetry. I think it's customary now that you always contract this SO6 index with some null vector. So make it null such that there's no trace path, namely the Konichi operator is removed. So this operator is a BPS. It has a dimension 2. This is the lowest dimension operator you have in the theory. And this is well known that the 2-point correlation function or 3-point correlation function of this operator are protected by supersymmetry in the sense that you can compute them by weak conjunction and the answer is correct to any order. The first non-trivial one is 4 points. So it's convenient to write the 4-point correlator as a say free part, namely by weak conjunction, and the remaining part as one we will be studying. And for the remaining part, it turns out the symmetry of the theory can decompose this into a factor which I call I, and I are completely fixed by symmetry. And the rest, well, I call dynamical part. So this will be the one people have studied. So for those who are familiar with amplitude, this prefect I is more or less like delta Q. Yeah. Anyway, so there's some factor you can factor out due to the symmetry, and we will just study the remaining. This is often called the partial non-normalization theorem. Right. So what do we know about this correlator? In perturbation, the correlator was well, even though there are a lot of efforts, so this was only computed up to 3 loops. And the integrand was constructed to 10 loops in the planar limit. And another important point that important and interesting point, which I will come back, that the non-planar contribution turns out that only starts to end at 4 loops, not earlier. So let me just briefly say how this was done. So the idea was that was using so-called Lagrangian insertion. So namely, if we want to compute this object at L loop, it's not surprising. So you just take a say L derivative with respect to the coupling, you bring down the Lagrangian, and so there will be relation like this. The important observation was that well, it's really, it turns out that you can insert the Lagrangian or insert the Cairo Lagrangian. The difference is just by total derivative. If you insert the Cairo Lagrangian, the important point that the O2 and the Cairo Lagrangian are on the same supermultiplier. So this object turns out has SL plus 4 symmetry instead of S4 times SL. So now it's SL, S4 times SL. But they found that there's a so-called hidden permutation symmetry. So this object has a huge permutation symmetry. And furthermore, you know, since this is a 0 level, this is 0 loop, so namely it's computed by weak conjunction. So you know it's a rational function, and basically you know what kind of pole it has, you know the power counting, and impose this permutation symmetry, and impose further some conditions like some limiter, how this is related to the amplitude, and so on. And they were able to determine this integrand up to 10 loops. So again, to study, say, SO2Z symmetry, so we were interested in exact results, namely exact results with a finite coupling. including GR-MUS and the theta angle. What was known for that? We know in the larger angle expansion up to I call sub leading order, in the sense that compared to the supergravity term. So say supergravity term is 1, then this will be 1 over n to the q. Okay. If we translate it in string theory, so supergravity will be Einstein-Hilbert, namely R, and this term will be d6 out of the 4. And this is exact results, which I will review, was derived by studying the integrated correlator, which I would do it now. Okay, so just given the name, so integrated correlator, it just you have correlator, this object, it's a function of cost ratios and the couplings, and the dependent gauge rank of the gauge group. You integrate it over some measure. Of course, random choice of the measure will not help you. For instance, if we choose this to be 1, this integral, I think, is not well defined. It's divergent. So one measure was found originally in these papers. Well, actually, I changed a little bit. But anyway, so this was originally found. Take this form, divide this in the spherical coordinates. When I saw it first time, actually, I didn't get any feeling. But of course, it was derived from localization, but I didn't get much feeling. However, by a simple, you have spherical coordinate, you can write it back to say 4-dimensional integral. Just combine theta and so on to make it a vector. So here I just introduce instead of UV, so I imagine UV come out of from say some kind of 4-dimensional momenta. So V I call it PV, and the PV squared is V, and the U there's a PU, but PU is related to say momentum conservation. So there's 3 momenta, for instance, and the P squared.
In the first integral, what is theta? Is a V?
Theta is related to UV like this.
All right.
Right. So yeah, that was the original. Say if you open the original paper, well, again, I slightly changed it, but it's the same thing. Yeah. So the next slide really it's simple translation. It's easy if you start from the second line, you can easily go back to the first line. But once you write it in this way, it's so clear what this integrated correlator does for you. So suppose you have, say, a Feynman diagram like this for the correlator. And the integrated correlator, what it does, so it really simply, you connect this to, as I draw here. And due to the momentum conservation, so then I should insert the P as well. So that for the first case, that's all integrated correlator does. It sounds innocent. Then there's a so-called second integrated correlator, almost the same, but you insert another object I call D111. So this I took it from the original paper. So this is the so-called D function, if you're familiar, ADSLT. But D111 is simply a box integral. Okay, so just insert another box. That's it.
Is it finite? I mean, do you hit any?
It's finite. Yeah.
It's finite.
Yeah, it's finite. Right. I even gave an example here. Right. So yeah. So like for this ladder diagram, in fact, ladder diagram is part of the answer to this correlator. And in fact, at 1 loop and the 2 loop, ladder diagram basically is the answer. So for the ladder diagram, the answer is famously known, given by this kind of say generalized Groher-Wigner function to any loop order. Then the diagram where you do this procedural integrated correlator, like this one, the answer is also famously known, and the answer is simply given by zeta or the zetas. So as you see, it's much simpler. And okay, right. So again, so this is not how usually they introduce the integrated correlator. And the point that with this particular choice of measure, this object turns out it can be computed by supersymmetrical localization. And so let me just briefly remind you the procedural localization. So we want to compute, say, some partial integral, and so to do that, well, for some case, so you deform the partial integral by some deformation. I got delta v here. If delta v obey, well, if delta is the symmetry of the action, and if delta v obeys this condition, then it's easy to see that you take a derivative and you see that this object will be vanished, namely this is independent t. Therefore, I can compute this deformed partition function for any t, especially I can compute at t equal to 0 or t equal to infinity. Where at t equal to 0, of course, this was the original partial integral you want to compute. Now at the t equal to infinity, if you choose your v and the delta properly, such that the bosonic part of that is a positive definite, then the partial integral will be dominated by a submanifold which obey this condition. And for some case that the submanifold is finite dimensional, right? So then this is reduced to a finite dimensional integral, and that's the case of N2 star to Yamures. So let me just remind you again. So we want to compute the correlation function in N4 super Yamures on R4 flat space. But nevertheless, so let me begin. Say N4 N2 star on S4. Okay, slightly away. So proper detail is not so important. So this theory, N2 star, is basically N4 super Yamures deformed by some master. Okay, and well, it's given here. So let me not bother with so much details. And well, the only point, which is the obvious point, is that when you take the mass to 0, obviously it will go back to N4 super Yamures. Okay, so keep that in mind. So the partition function for this theory was derived and was known due to the work by many, especially Nixoff and Paston, goes through the localization procedure I mentioned. And so they were able to say write out exactly the partition function for this theory on S4 and it takes this particular form. Often this got classical part, and this is one loop, and this is which gives a contribution to perturbation, and there's a non-perturbative part, the incenton sitting on the south pole and north pole of the S form. Okay. So to be explicit, the perturbation term is given by this Panos G function, takes this particular form, and the non-perturbative part, the incenton. So you have the incenton on the south pole and the incenton on the north pole. So it's product of incenton and anti-incentons. And for the incenton, I can write it as 1 plus sum of the number of incentons. So K represents the number of incentons. So ZK represents the K incenton contribution. All right. So again, so to be explicit, the Nixoff partition function for the K incenton contribution, well, takes this particular form on S4. So there's a formula for for the so-called squashed S4, where you keep there's a squashed parameter epsilon to be general. So here I already said the epsilon 1, epsilon. There's epsilon to be 1, so it's on the rounded S4. So this counter integral pick out the poles, where the poles is given here, and so R and S. So AJ, well, sorry, I should remind you. So AJ is the variable integrated over, this so-called Coulomb branch variable. Then there's R plus S. So here I is an imaginary number I, where R and S basically the position of a box in a Yann diagram. So let me just give you examples. The first non-trivial example, say 2 instantons. So the point that there's a Yann diagram, say for SUN theory, where you have basically the point that I want to distribute the K box on M positions. In this case, there are only 2 boxes. So you can put these 2 boxes on the same position, like this 2, or you can distribute these 2 boxes on separate positions. Right? And in general, for general K, as you can imagine, the situation is very complicated. You have to draw all possible Yann diagram, then you have sum of all those residues. So so already this is a very complicated object. Okay, so I went through a little bit about the localization, namely the partition function for this this particular theory, and go to 2 star super Yamu's on S4. The reason I introduced that is because there's a relation between this integrated correlator I introduced earlier and the partition function. The relation is simply that you can take 4 derivatives with respect to the parameter in the theory, so you can take 2 derivatives with respect to mass, and that's why I introduced the mass. Then you take another 2 derivatives with respect to the coupling and set the mass to 0. So remember, I mentioned that when you take mass to 0, you go back to N4 super Yamu's. Or said in another way, you take the partition function, you expand it to the mass to the 2nd order. The first order is trivial, just like 1, then the 2nd order. It's not that surprising, there's a relation between correlator and the 4 derivative with respect to the partition function, because when you take a derivative, you bring down operator. But you bring down operator integrated over, right? Because so I'm sorry, let me just so the mass depends on something like this. It's integrated over. So when I take a derivative, you may bring down this guy, you may bring down this guy, you may bring down this guy twice if two derivative. So taking derivative with respect to mass, you bring down a bunch of operators, and similarly taking derivative with respect to tau, you bring down some other operators. Okay, but what we want is not any correlator. We want this particular correlator, right? The 4-point correlator of those operators. So, but if you just take a derivative, you bring down, as I said, bunch. I call JK, whatever it is. It's not the same as O2. But of course, you can use the supersymmetry and superconformal symmetry to relate correlators of those operators with this guy. So do that, you will generate a lot of factors by relating different correlators. So not surprising. Second, we are doing this partition function was defined on S4. So I have to do a conformal map from S4 to R4. Doing that again generate some factors, and the statement that when you combine all those factors together, you will find this particular measure. I always feel maybe there's a simple way to derive it, but anyway, this was how it was derived originally. So let me look up. So there's a simple relation between this integrated correlator and the partition function. Okay. So it turns out that you can, take 4 derivatives with respect to other parameters. Say I can just take 4 derivatives with respect to mass only. That's the other integrated correlator, and people work it out that. Let me just remind you. So the measure is this guy. Okay. Sorry. It turns out that there's another one. You can take a 2 derivative with respect to mass and the 2 derivative with respect to the squash parameter, which I set to 1 when I write out when I say epsilon 1 equal to epsilon 2 equal to 1. But you could keep it and you take the derivative with respect to that. I think the measure associated with this integrated correlator has not been worked out. So in this talk, I will mostly focus on this one. Turns out this is the simplest one. I will also discuss a little bit about the 4 derivative with respect to mass. Okay. Any question? Great. Okay. So let's be concrete. So first, let me begin by computing this this object perturbatively, in the sense that I take the perturbative part.
Still, to work out this measure, is it what's the problem exactly? Is it just hard to simplify to like?
Yeah, it's just harder to simplify indeed. So
to work it out, an ugly form is simple. Right?
To work out the what?
The ugly form of the measure is easy to derive. Just perfectionism stops you from claiming that.
Yeah, in principle, yes. Yeah. So, for instance, if you look at original paper, the measure looks rather much more complicated than what I wrote here. It has log and so on. Later was simplified. I don't know. Yeah, as I said, there's a lot of different objects here. When you bring down operator, there are in fact also 3-point correlator. Eventually, you have to try combine everything together to make contact with this one. So you generate a lot of different objects. Then you combine them. Yeah. And also, if you have a complicated measure which was not simplified, it made it difficult to study it. Right. So yeah. So to compute the perturbative contribution, so I could just take the Paston's result and set the instanton part to 1 and look at the perturbative part only. This is not difficult. Well, so I just basically gave you the formula, the integrated correlator using this result. You find it will be given by something like this. So as I mentioned, this is like n-dimensional, well, n-1 dimensional integral n-1 because it's SUN. So sum over AI is equal to 0. So in general, it's n-dimensional integral.
Sorry, could I ask, so this particular type of matrix integral, is it, can you solve it with orthogonal polynomial technique?
It is. So this was solved. Yeah. So for the perturbation part, you indeed can get a exact formula, rather as like 1-dimensional integral. Indeed.
So is that also the reason behind why you can simplify the derivative? You can use orthogonal polynomials and then reduce.
Yeah. For the perturbative part, yeah. I think it's a difficult. Well, yeah, I will come back to the instanton part. Right. So here I just focus on SU2. Yeah. So this 1-dimensional integral you can manipulate a little bit, but may or may not necessarily. Anyway, so the answer will be like this. And I introduce a new variable I call y. Y is used for just to get rid of the pi's. Okay, it's defined here. So this looks innocent, but anyway, let's study it. So we took this integral and expand in large Y and small y. So at the beginning, we'll just explore it. Okay, if we do that, that's the answer you'll find. Nothing fancy. Then here comes the important observation. We notice that these 2 coefficients for say large Y expansion. So large Y will be small coupling. So this is like loop expansion. So remember, y is 1 over g. Then there's a small y expansion, so this will be like a strong coupling expansion. And the observation is that we notice this two coefficient, the ratio of these two coefficient, actually are identical to the two perturbative terms of non-holomorphic Ison series, which let me just define you or remind you. So non-holomorphic Ison series is defined by two-dimensional lattice sum, it's just given here. So we sum over integers to avoid divergence. So m and n cannot be 0 at the same time. This object, you can do a Fourier mode expansion. Fourier mode in the sense that you expand the given for different phase. So tau 1, remember, so my tau, sometimes I call tau 1 plus I tau 2. So there's this term will really relate to the perturbative term, 0 instanton or 0 mode. And this part is the K instanton contribution. So here, this capital K is the base of K function. As you know, the behavior of this function, this goes like exponential, and that's precisely how the instanton behaves. Okay. So anyway, so here, this is the definition of the non-holomorphic Ison series. And if you believe me, these two coefficients precisely, well, the ratio precisely is identical to the ratio between these two numbers. So that led us to conjecture that this integrated correlator, at least for SO2, can be written. So I basically complete this perturbative term by promote it. So instead of saying, y, I promote it to be non-holomorphic Ison series. Okay. So by construction, this conjectured formula matches the perturbative term. Yeah, by construction, right? I constructed it such that it matches the perturbative term. The question, of course, is what about the instanton piece? Let me not go into detail. The check works out. So in particular, say 1 instanton, the computation is really not difficult. You can get the exact formula. It looks like this. So if you trust me, this object precisely agree with this infinity sign if you pick out the 1 instanton part. And as for the K instanton, so I mentioned this Yann diagram story. So if you do a general, say, Nicholas partition function for K instanton, it's really complicated. You have to sum over those Yann diagram, try to get any explicitly formula. It's not easy. However, remember, we don't want the complete Nicholas partition function. What we really want is simply expanded to the second order in mass. So what we want is just this piece. For that, in our early work, we were able to prove that for this object, not all the Yann diagram contributes. It turns out only so-called rectangular Yann diagram, namely, the diagram with this rectangular shape. For K instanton, so you want the rectangular diagram where you have, say, P row and the K columns. Only sum over such diagrams. So this simplifies dramatically. So first of all, you don't need the sum of all the diagrams. You just look for such diagrams. And for such diagram, we were able to compute the Nicholas partition function, just summing over those diagrams. Yeah, so as I try to emphasize, in general, the K instanton computation would be very difficult, but for this object, things simplified dramatically. And then we were able to compute it for arbitrary K. And the final answer will be similar to this one, much more complicated. However, the typical term will be like this. There are a lot more terms, but typical like this. And again, one can check now against the conjecture, and you find the perfect match. Another interesting point that so, as I said, the k-instance contribution is naturally decomposed into like p times q. So k naturally decomposed to p times q, and we found that if you take, say, if you take q equal to 0, let's say, and you sum over all the p, well, q equal to 0 implies really the 0 instanton, k equal to 0. And we found that actually this result will match with the perturbative result. That's not obvious at all if we just look at the, say, Nicholas superposition function. By comparing the Nicholas superposition function and this perturbative part, which is given by genus G Barnes function. It looks very different. However, when you compute it explicitly, well, at least for this order, we found that there's a very simple relation between instanton part and the perturbative part. And it should be because they are related by SL to Z. Okay, so we conjecture, then I try to argue this conjecture is correct, that the SU2 correlator can be written as basically infinity sum of this non-holomorphic Ison series. So now you can figure that, yeah.
Can I ask a question about this previous small and large Y expansion, and when you rewrote it with this Eisenstein series? So it is a asymptotic series, right?
That's correct.
Okay, so and then you rewrote it through this Eisenstein series, which contains exponentially small terms. Not
exponentially small term in the sense when Y is large, yeah.
Yes, in large Y a limit, so you have a asymptotic series, and you rewrote it with this in this way. So it means that so if you just sum perturbative part, I mean perturbative in 1 over Y, so it will be not barely summable.
So this is Boole summable.
Yes, but for large Y.
This is also Boole summable. So,
it's also summable.
So they are both summable. The reason that there's a -1. So this is a typical.
Okay. They are barely summable. Then. Okay.
So yeah, because of this alternating sign, the pole is on the negative.
Yeah. Then no question. Okay.
Yeah, of course, you can think of this as a formal.
Can I ask a question? Actually related to the previous one, because there you also wrote a term which corresponds to small Y expansion, yeah?
Right.
But the expansion of the Eisenstein series, which you showed, you just said corresponds to large Y expansion. So.
Oh, no, sorry. No. So this is just a Fourier mode decomposition for any Y. So this is like, I decompose for whether or not there's a phase.
Yeah.
It's not the expansion, and just take this result doing a Fourier mode expansion.
But then why can you ignore these red terms?
Oh, sorry. No, I'm not ignore the red term. So I was saying, say for the 0 instanton Procedural localization, I found that the answer takes this form. Then I compare with the non-holomorphic Ison series, just compare to the perturbative part. I found, these two coefficients are identical to these two coefficients.
Yeah, but my question is, so suppose you want to extract a small Y expansion of the Eisenstein series.
Right.
So then you use essentially you are saying you use this Fourier expansion, yeah, and you claim that the second term is the leading one. Is it correct?
Yeah, you could say that. Yes.
But then my question, well, by saying this, how do you see that this is indeed the leading term? In particular, why you can ignore the last term, the red one?
So
do you see this explicitly?
Right. So first, let me make clear. Here, I'm just considering perturbative term. Okay, so
Sure.
I'm just making some observation. I noticed the perturbation term, match this perturbation part of Ison series. This formula I write it down now is a complete complete result, complete in the sense that include all the instantons. So this is valid for arbitrary coupling.
Sure.
Let me ask a question or make a small
simple.
comment. Okay, sorry. Isn't
Yeah.
it just a statement that this Eisenstein series, at large y and small y, they are related by weak strong duality, right?
Yeah.
So they are approximated by the blue terms both at weak and at strong coupling.
Yeah.
It's not so different, the expansion at weak or strong coupling, right? They
That's
are trivially
correct.
related.
Yeah, indeed. So I was that's why there's a 1/4 instead of 1/2. So in a sense, these two have the same thing because it's expansion of the one function. So I take this one function, I expand it in a different way. I got two different expressions. I noticed these two expressions appears in Ison series, and so when I replace this function by Ison series, indeed I put a 1/4, namely divided by 2, because as you said, these two things I think of as an identity object.
Sorry, still then I have a question. If it's invariant under S duality, I would expect just apply S duality to the leading term and get the other one, yeah?
Well, S duality you should include the instanton part. So the whole thing, S duality cannot relate the perturbative part only. So the whole thing is SO to the invariant.
Sure.
So,
Just the question, because Pedro suggested that the two expansions are related by S duality. It means that the leading term.
Not exactly SO to the duality. You see, when y is, as you say, when y is large, this guy is exponentially decay. When related to y is small, this will become important. The instanton part will be important. Right. So S duality.
Yeah, sure, I agree. Actually, my original question was very simple. What is the small y expansion of the Eisenstein series? Is it true that the leading term is the second term here?
Small y expansion. Yeah, the leading term is this one. Yes. Yeah. So this will be just basic function. Yeah. So I think it's the leading term is this one. Yeah.
Well, just my claim is that you cannot draw this conclusion from this Fourier expansion because the red term, as you just said yourself, is important in the small y limit. So.
Sorry. As I was saying, here it's zero Fourier mode, so k to 0. So they don't mix each other. You see, and just look at the k to 0 sector, right? Even though you say, okay, they are the same amount, it's not important to me. This one has 0, this one has 0 Fourier mode, k to 0. This has a different k. Even this one dominates over that. It's not important. I just look at the 0 mode and compare them, right?
Okay.
Not really, no. I think it's related to the 1/4 factors that you were pointing out, right?
1/4.
I mean, it's not true. I mean, you can write this Eisenstein series in a way that makes manifest either the weak coupling or the strong coupling behavior, right? To go from one to the other, you need to reshuffle things a little bit. Am I right, or am I missing? You can write an expansion where it manifestly you make one behavior manifest, another one where you make another behavior manifest. Of course, they are related, but there are some numerical factors, and I thought that was why you had these factors that you were explaining.
So I began with this function. Right? This is just one function. Right? So again, let's just focus on 0 mode, k to the 0 factor. And I began with this function. And well, I do, it's the same function, right? Just one function. I expand it in this way, I expand it in that way. Then I notice, these two objects appear in this thing. Well, I call this thing as E. Well, let's forget the red part. I call this thing as E. So then I just you know, it's a bit of then I write this function as a, in some sense, I write this function as a sum of these two objects. Of course, it's a formal. It's a bit of formal. I take this function, and I say this function is a sum of the small y expansion and the large y expansion, and divided by 2. That's what I did. Right. So I don't know if I explain myself. So I have this G, and I expand it in large y, I expand it in small y.
I think,
then I
question,
start them.
I think the stand what I think Sergey is asking is if you put a number 0.01, will you get an agreement or no?
No. So this is of course just formal expansion. Yeah, no, of course well normally you wouldn't do that. I cannot stand.
Why not?
No,
Why not? If you claim that a function is equal to another function,
sorry.
put a number and check.
I should have put a tilde. So this is not the final formula. It's a formal sum. There's a lot of problems. So as always, you know, you have infinite sum. You should be really careful.
I cannot.
Right, let's move on.
Can I ask a question?
Okay, yes, please.
So you have this one-dimensional integral formula for G2, right?
Yeah, that's what
Does it
coming to.
manifest that it has y goes to 1 over y symmetry?
So yeah, so this is manifestly SL2 invariant.
Okay.
Yeah. So sorry, let me just come back. So again, you know, as always, infinite sum, it's dangerous. It's not. I should have put a tilde here, right? So it's just formally. It's some observation formally. So eventually, I will make it really well defined, and well defined is through this resummation. I hope that helps.
Yeah, so maybe the simplest thing to say is you could have just not motivated this, right? This was just motivation. You could have just presented us with this expression and then said, look, I expanded at one limit and I expanded at another limit, and it matches in both cases. But then we would have been completely puzzled because we would have said, how the hell did you invent this crazy function?
That's exactly right. Exactly. So yeah, I could, you know, I should have put all the tilde here. That probably better. So, well, I was careful to put the tilde everywhere previously. I should put the tilde here. So yeah, so just think it's some motivation for the final expression. Okay. Right. So yeah,
So which one is final? Just to clarify, because
I haven't gotten to the final yet.
All right.
Right. Okay. So we were here. We were somewhere here. So this was motivated from the perturbative part. I should also say, when I say check instanton, I skipped a lot of details. When I say check instanton, I need a sum over. I have to do an infinite sum. I lie a little bit. When you do infinite sum, I have to regulate and so on. Or as I said, I could present this formula from the beginning. So anyway. So since I began this way, so I motivated this formula, which I'm sorry, so we should think of that as a formal sum. Then I use the definition of the non-holomorphic series. So I just plug it in and using string parameterization. I write here. Then I can do the sum. After the sum, that's the formula. And the claim is that this formula is all well defined. It's still sum, but it's well defined. Now you can take, say, large y expansion, small y expansion, or look at the instanton sectors. They all agree with whether you would compute the from. Well, sorry, whether you would compute the from. Oh, sorry, here. That will agree with whether you would compute the from localization. Okay. So as Lance asked, so this formula, this particular combination, it's easier to prove that once you sum over the integer is manifest SL2 invariant.
So sorry, just to again to clean the logic a bit. So from localization, you already got one-dimensional integral, and that's end of story.
Or for the perturbative part.
But instant, okay, instant on.
You have to sum over, as I was saying, you have to sum over all those Young tuples and so on.
All right, and now you like by doing all these tricks, you completed it with instanton. That's what you're claiming.
Yeah. And I think one important point that it make manifest the SL2D invariance. So, as I was trying to emphasize, yeah, SL2D would not manifest. Okay.
But each separate instanton contribution is also one-dimensional integral.
No, for a given k instanton, you have to sum over this k box. You need to know.
Yeah, okay, it's sum of k integrals, which is one integral.
Well, it's not a sum of k. Well, so this residual k-dimensional residual integral, or yeah, you can think of this as a sum, but yeah, it's a k-dimensional residual integral for arbitrary k.
Mm-hmm.
Yeah. Right. Okay, indeed. So I could, present this formula and say, then you take a weak coupling expansion, strong coupling expansion, or instanton, and it matches what's known from a localization. Okay.
Okay, good. So actually, it seems so that we had already coffee break discussion. Maybe we will have now 3 minutes of coffee break.
Okay.
Just to let people few minutes. And we can pause recording.
Right. So.
All right. Thanks again. Right. So I discussed the SU2. Let's now move on to SUN. So as I said, it's a conjecture. So we were not able to prove it. I think for perturbation part, that's purely perturbative. Probably you can prove it. We didn't try, but I think you can prove it. Yeah, indeed, you can prove it using this orthogonal polynomial story. But again, the difficulty is an incident part. Anyway, so we studied a lot of examples. Then we came out with this conjecture. So the structure is clear. So I think, first of all, this formal sum, let me emphasize it again, is very helpful. You have this idea, this expander in terms of Ison series, it's really helpful. And then from that, basically, again, so you plug in the definition of non-Holomorphic Ison series in this Schwinger parameterization. Immediately, you will conjecture a formula like this for arbitrary n. So basically, this is a generalization of that.
So can you remind what are the orthogonal polynomials for this for perturbative part?
It's called Laguerre. Is it called Laguerre polynomial?
So it's not what you get.
No, it's different. Yeah. So I think there's a way maybe to relate this one. So the perturbative part was computed by Chichester. It's a bit more complicated than the one I'm presenting. Well, these two things are not directly related, first of all. But anyway, the expression he had in terms of this, like a polynomial has a sum. Here we just a single Jacobi polynomial. In fact, this one can even further simplify, which for some reason I use this one. This can be related simpler in terms of hypergeometry. Right. So by studying a lot of examples, so we found some kind of pattern. Eventually, we conjecture that for arbitrary n, this object can be written in this form, where basically all the dynamical parts, in some sense, is given by this object we call the Bn, and Bn takes this form, and there's a numerator which is a polynomial, and polynomial takes this form. Okay. Okay, let me just give you some feeling. What is this? SU2 I already discussed. This object takes this form, and SU3 it looks like that. So one thing you notice, it's a symmetric, where the highest degree and lowest degree has the same coefficient. It's always like that. This symmetric property, and with this right power here, implies we call it inversion invariance of this rational function. So this property is deeply related to the, as you can guess, deeply related to the SL to the property. Furthermore, this object based on integral identity, which turns out to be important for me to do this Poisson summation and so on, but I won't really do it here. Anyway, there's some important property about this object. Probably most importantly, so this also looks a bit random. A array following simple, say I call it differential and difference equation, namely related Bn with Bn plus 1 and Bn minus 1. Okay. Why this is important? Because using this differential equation for B by integrated by part, now you can convert this differential equation for the differential equation for G, the correlator, well, precisely the integrated correlator. So it's not difficult to check. I just claim that once you use that and do it integrated by part, you will find that the integrated correlator obey following, I think, very simple Laplace difference equation. Well, so the Laplace is defined on this hyperbolate, and so this equation relates the correlator, for SUN theory with SUN plus 1 and SUN minus 1. Just to give you some feeling, so for non-holomorphic Ison series, which I introduced, they obey, well, this relatively simple Laplace equation. So this one like that. Okay. So in particular, say if you give me the initial data, namely G2, this equation will determine you for.
So this holds separately for perturbative and instanton part.
That's correct, because you can do it like a Fourier mode by Fourier mode. Yeah. So from now on, I will just study some property of this object. So the first thing, obviously.
Sorry, can I ask a question? So now that you got this beautiful equation, can you derive it from its definition? Could you have derived this? Would it be possible to start with the original definition of this G and recognize it?
From localization, from the localization. Yeah, again, it's a bit maybe, I don't know, to me it's difficult because it's relating, n-dimensional integral with n plus 1 dimensional integral.
But isn't it just one of the integrals, no?
Maybe, yeah, maybe. Yeah, it may be. Yeah, but once you do that integral, you want to bring into the same form, right? I don't know.
It looks more like a determinant expansion, right? So that's why for free part, it kind of should come out immediately from all the orthogonal polynomials stuff. But can I look? You have the G written as some integral transform of this Bn, right? So can you inverse this integral transform and act on the initial expression and then just read off Bn?
Sorry. So I have this. You mean this formula?
Yeah.
So then, what do you want to do?
Bn is there, right? It's in the slide.
Right?
Bn.
So can you do inverse Laplace of Gn?
Inverse Laplace of Gn. Yeah, maybe, yes. So
and then so your prediction is that inverse Laplace transform of Gn is super simple. So let's act on terms separately and read of Bn probably.
You mean starting from this equation to derive the Bn?
No, from the definition from your n dimension.
Definition. You mean definition? You mean from localization, the Nicholas-Orr partition function?
Yeah. So your prediction is all dependence on taus is hidden in this Laplace transform factor. So you can get rid of all dependence and then you just get T parameter. And your prediction is that Bn is very simple, so you should see immediately some simplification. But Okay, so conjecture is conjecture. Why do we need to prove them? That's stupid.
Yeah, maybe that's infinity sum. I don't know how to decompose. Maybe. Okay. Maybe. Okay, maybe. I don't know. Yeah, but right.
Can I also ask a question about this relation, recursion relation? Is there some explanation on the level of field theory? So somehow it relates n minus 1 with n plus 1, and
That's
so
right.
it is free.
Yeah.
So is there any ideas what this relation corresponds to on level of field theories? What relates them? Is there something?
They're only related at the level of this specific quantity, not that they're always related.
Oh, that's the question. It is just something specific, or maybe there is something behind that on level?
Yeah, no, for this special correlator, or for this special integrated correlator. So there's another integrated correlator, which I will probably discuss shortly. They don't satisfy the same differential equation.
Don't?
That the other integrated correlator with a different measure.
Yeah.
And that guy does not satisfy this.
Okay.
Sorry, just a very naive question. Actually, since Volodya is also in the audience, but aren't these type of equations very common in matrix models and derived with some ordered identities? And the starting point is like a matrix model, right?
It is, yes.
So I would imagine that people that are experts in matrix models see this n plus 1 and minus 1. Wasn't this, I think?
Okay.
It's just the fact in orthogonal polynomials, this become a matrix integral become a determinant. Then this is just a relation between determinants when you expand it.
So in particular for the perturbative part, I believe one can just prove it. Take this orthogonal polynomial by Schweitzer. So in the perturbative case, so this instead of d tau just d tau bar just d tau 2 derivative with respect to tau 2. That's it. I'm pretty sure try harder, take his formula in terms of this Laguerre polynomial, probably you can prove it. But yeah, so again, to me, maybe the complication is instanton part. Right. Okay. Right. So let me just now start to play with this object. So let me begin with perturbation. So now you have formula, then obviously I can just expand it to any loop I want for finite for any n. So here I introduce A is just to hold the coupling divided by pi's. So one thing is that well, you notice it's simple. It's always given by all the zetas. So in particular, we want to check, our object does agree with the standard perturbative result. So as I mentioned, the result was known at 1 and 2, sorry, at 3 loops, and the integrand is known to 10 loops. So in the case of 1 and 2 loop, we plot this number, or this zeta 3 and zeta 5, and predict this particular number are indeed in agreement with the perturbative result. So namely, if you take the perturbative result and you integrate over this measure, you got to precise those numbers. 3 loop, you can do it, say, numerically, but I don't know how to really prove it, or even higher loop. So one can, for the planar guys, the integrand is there in principle. Maybe one should be able to do it to check those numbers. So we haven't really done it. The other property I already mentioned, that it's a known fact. People found that for this 4-point correlator, the non-planar contribution only starts to end at the 4 loops. That's a non-trivial fact. And indeed, we see that the non-planar term starts to enter here. And in fact, the non-planar term, the next one actually always enter up to every 2 loops. So namely, the 1 over n to the 4 does not start here, but instead it starts here, and again n to the 6 is again begins at say 8 loops instead of 7 loops. Such a property also was observed by others when they compute the form factors. So this property are again in agreement. Of course, this gives say all loop prediction for any n, and we should try to check it using comparing to more standard methods.
Congkao, do you get this formula for all n at once, or do you get it for one n after the other, and then you fit it to a formula that has this independence?
All n at once.
Okay. Thanks.
Yeah. Sorry, where is it? Right. Then we also studied larger n expansion. So this will be like genus expansion. And then you can study say small lambda, or standard to Holter, and or large lambda. So well, anyway, so this is a formula you can find. Say you do genus by genus. I forgot how far we go. We don't have like arbitrary order, but we can go pretty high if we want. And we always find this theory is convergent with this finite radius. And this property, I think, has been seen in many places when people study n-for-super Yamuos. And since it's convergent, you can just even resign it. Due to those zetas, actually, resign is not trivial, but you can replace zeta by Symmetry and so on. And once you do the resign, you find that answer. And again, so this was originally computed by the first paper using different method, where they write as say base LG, but it turns out there's a relation between base LG and the hypergeometrical fancy agreement. Again, so here we can actually go very high if we want. We did actually. Then you can also do say large lambda. So again, large n expansion instead of small lambda, you can do large lambda. So we want to see the property. And now the big difference, as you can see, there's alternating sign. So always alternating sign. So this is an indication whether or not it's Boole summable. Well, this case it's convergent. So here there's no alternating sign, and turns out this is not a Boole summable. Namely, when you do the sum, you find there's a singularity on the positive axis. Well, in this case, you can run the procedural resurgence. So we actually compute exactly, well, we have exact formula for all of the coefficients. Anyway, we found the exponential term, say, to complete this function, due to the fact that it's not a Boole summable, takes this form. And particularly, it goes like exponential 2 square root of lambda. Again, similar behavior has to be seen in other quantities or n-for-super Yamuos. So if we want to translate it in string theory, so this is square root of n, and this will be like alpha pi, 1 over alpha pi. I guess that's indicating this is Wirth-Schütte instantons.
But for example, cusp anomalous dimension.
That's correct, yeah.
And
also
it has a similar structure.
Right, I guess the power different, maybe 1/2 cusp. Then the some quantity computed by Lance has factor 1 here. Slightly different behavior.
So where are these? What are these Wirth-Schütte instantons wrapping?
Yeah, good question. I don't know. That's what I'm saying, indicating. Okay. But just from the power counting, yeah. So there's in this file, I cannot have cycle. Maybe it's because the points, the points for the correlator. Yeah, I don't really know, but yeah, just from the power counting, that yeah, I don't have any concrete answer to that. Right. Finally,
Can I precise, when you wrote resurgence analysis, it means that you really checked that in this non-variable case, this ambiguity in the resummation of perturbative is exactly cancelled by non-perturbative terms.
That's right. Yeah.
So you checked it explicitly, yes.
Yeah. So basically, if you do the sum, you find that this will be like a hypergeometric function, which has a cut on the real axis. Then you have to take the discontinuity just following the standard procedure. Right. So the final limits I would like to take as a larger angle expansion by the finite coupling with finite theta angle. To do that, what we did is try to do larger angle expansion for the integrand, this Bn. And well, anyway, if you expand it, well, normally, you cannot just expand the integrand. You should integrate. You should expand the integrate result. Right? But it turns out, well, we analyzed carefully. So in this case, it's allowed. You just expand the integrand, and you got the right answer. Well, anyway, so if you take that rational function, you expand it in that thing, you find it takes this form. Then you plug it in back to the integral and translate it into couplings. Each term basically turns into non-holomorphic isosceles. But so let me see again. So if you do what I said, the larger angle expansion of that integrated correlator again is expanded in terms of non-holomorphic isosceles, but now with a half integer. So previously, it was a it was a formal sum. Emphasize again, and it's summing over integers. But somehow, when you from finite angles to larger angles, the translation. Well, transition, this became half integer non-holomorphic. And furthermore, well, at each order of one-way expansion, that's only finite number of non-holomorphic.
Can I have a question?
Right.
So these E3 halves and E5 halves also appear in the amplitudes in flat space, right? As the first term in the energy expansion.
That's
correct. But here,
I will make a connection.
Okay. Are these 3 halves and 5 halves in the first line the same 3 halves and 5 halves that appear there?
That's correct. So this will be R to the 4. It's a D for R to the 4. Yeah. Right. So yeah, at this moment, I just take the correlator and expand it in larger end. So well, some of the result actually was already appeared in our first paper with Pufu and others. By then, we were very puzzled by those random numbers. Now, I mean, the random rational numbers. Now we understand that those numbers appear in such a way that they obey the Laplace difference equation. So said another way, I could get this result by solving the Laplace difference equation order by order in 1ON.
So sorry, this large n expansion of the integrated correlator.
That's correct.
So what's the expansion? How come you get these weird powers if you think in terms of planar expansion?
Weird power, you mean square root n?
Well, I mean, if you have a correlator in a gauge theory and expand in n, you expect 1 over n square expansion usually, right?
Sorry, can you say again? What do you expect?
We can have a gauge theory and expand in large n some correlator. Normally, we get 1 over n square expansion.
So, no. So here's the difference. So I think you had in mind like this one, right? This is what you were thinking.
Yeah. So what was this?
So the difference is that this is more like the whole expansion, what you said. But the expansion I'm talking is a finite coupling, finite GR mules.
So if you take your expansion and expand perturbatively in lambda, somehow the powers in the recombine to give the one.
If we want, indeed. So you can also see this way. as Lance said here. So indeed, so we can just from perturbation. So I do the normal expansion, take lambda, and that's the behavior you have in mind. Then if we want, I re-express my lambda in terms of n times g mu square. Then you will see square root of n coming. But well,
but again, if you think in matrix model from which you started, so non-perturbative will have a matrix model. If you forget about instantons, it should also give 1 over n square expansion.
No, yeah. So here I didn't include the instanton. So this is just perturbation. But that's the answer you got. Yeah. So again, if you keep a lambda and n, the expansion is what you said.
But like lambda is just parameter in your matrix model. Normally, if you have like, I don't know.
Yeah, but lambda is combining with g. Matrix model was originally written in terms of n and g, not the lambda.
Okay, I see. That's fine.
Right. I could go back if you want. Since it's more well, so this is like g. So this is 1 over g squared. There was no lambda.
Like kind of explicitly introduce some independence into the matrix model parameter.
Yeah. Right. Okay. All right. So if I keep it, g or tau, then expand n. That's what we found. Okay, yeah, so now I try to make a connection with a string. I don't know if I take too long, but maybe you can stop me if it's so let me just remind you a little bit, say the string amplitude. So here I will just study low energy expansion. So that will make a connection with the larger n expansion. In the low energy expansion, string theory correcting Einstein-Hilbert action. And it turns out that supersymmetry disallowed, so R squared and R to the Q are not allowed. Then the collection began with R to the 4, and say T4 R to the 4, D6 R to 4, and so on. The question was, well, I guess the first question was, what is R to the 4? You have the index to contract. But anyways, they are fixed by supersymmetry, including those ones. The Laurent index contraction are completely fixed by supersymmetry. Now the second question is, what are the coefficients? The coefficient, of course, depend on the string coupling. Well, say you could compute them explicitly by genus by genus. Say take a genus 0, where you can just take via Solo Shapiro amplitude, expand in alpha pi. And the first the first guy is just supergravity. So this should be related to R. So 1 over STU, probably you saw it. And then the next one is R to the 4, this one. And then there's D4 R to the 4. So this is related to the 4 derivative. Then you have D6 R to 4 related to the 6 derivative. Okay. And the coefficient at the genus 0 just shows zetas. So I already used this delta Q. Well, it's done due to supersymmetry, and you can think of delta Q as R to the 4. I should also mention that this delta Q is precisely related to this I in the correlator I discussed long ago now. When I introduced I mentioned that it has something to do with delta Q. Anyway, so you could compute this like, well, in principle, genus by genus, and study instanton contribution. In fact, recently, Ashok was trying to compute this instanton contribution directly. But anyway, so it turns out you can use the symmetry to constrain those coefficients. That was originally done by Green. Later, people derived it using amplitude techniques. Anyway, the conclusion was that the coefficient of R to the 4, D4 R to the 4, D6 R to the 4 are completely fixed. They're given by E3 half, E5 half, and in the case of D6 R to the 4, it's given by so-called generalized non-holomorphic Ison series. Just to remind you, so Ison series obey this simple homogeneous Laplace equation whereas the generalized guy obeys the inhomogeneous Laplace equation. The change looks innocent. However, the solution to this equation are much more complicated compared to that one. Particularly, this contains so-called instanton and anti-instanton pairs. Rather, this one, you only have instanton or anti-instanton separately. But this one has much more complicated structures. Now I can start to compare with the integrated correlator. So the statement is that, again, so larger N expansion is related to the alpha pi expansion. So the leading term is basically the integrate supergravity term. And the next term is integrate R to the 4, but now, of course, on ADS5 cross S5, and you can go on. Okay, just by power counting how alpha is related to N and so on, you figure it out. One observation is that for this integrated correlator, one thing you notice that it only has half integer n. And those half integer n, well, the integer n, which doesn't appear, if you do the power counting, they associate high derivative term of this form. In particular, the n equal to 1, that will be d6 R to 4. So d6 R to 4 never appears here in the sense that they integrated to 0. Namely, if you take a d6 R to 4, you integrate with that measure, you're supposed to get a 0. To see those guys, turns out you have to look at the other integrated correlator. Yeah, the only thing I try to emphasize, this one is more difficult to compute, but nevertheless, we compute a few orders in the larger N expansion. So there's no, say, finite N expression for this one. And for the larger N expansion, then we get some information about those high derivative terms. Again, on integrate and on ADS5 classify. Okay, let me just flash the expression for this object for larger N expansion. So now you see this has a half integer n and integer n. And for the half integer n, half integer expansion, they are again given by non-holomorphic Ison series, and the coefficient changes. And for the integer guy, they're given by this so-called generalized non-holomorphic Ison series, which is, well, particular coefficient. Anyway, so from those results, now you can actually reconstruct. So I have been talking about the integrated correlator. Now you can try to reconstruct the unintegrated correlator to put back the space-time dependence. And the idea is that you try to write the ansatz by some knowledge about this correlator, and try to fix the ansatz by comparing the integrated results. This can be done most easily in Milling space. So here I introduce the Milling amplitude. So this is a correlator. It's related to the Milling by some Milling transformation. And this object is often called the Milling amplitude.
Sorry, just to understand something about the logic. So you are presenting this as a second step, but this is the first step, right? To derive the results of the previous slides that you just showed on the relation to flat space, you had to go through this path, right?
You mean this result?
Or even the previous one, when you said the integration of this R to the 4 gives this.
This result, yeah, indeed. But this result, I really didn't. In some sense, I didn't use the ansatz. I just make a use of ADS-LT. I'm just saying by power counting, say alpha pi, like which alpha pi.
Okay, but to get the precise coefficients with the 3 and so on, you need to go. You need to.
This coefficient come out from localization.
I understand, but to relate precisely to the coefficient of the amplitude to the coefficient that appears in this integrated correlator, you need to go through what you are now explaining, right?
That's correct. So here I'm just saying this -3 over 2 to the 4 should be, according to ADS-LT, R to the 4 when I integrate all this measure.
Mm-hmm.
Indeed, I will use this information to fix it. Right. So so this Milling amplitude, I can make ansatz by knowing, well, this is supergravity term. People already compute it. I just pretend I don't know. But in principle, I could fix it by knowing the pole. Pole is just telling me, what does operator exchange, right? So say that arbitrary coefficient. Then there's a R to the 4. So R to the 4, because I use the supersymmetry, I already removed the R to the 4, so R to the 4 became just constant. Then there's one loop by gluing, say, supergraviton. Then there's D4 R to the 4. So D4 R to the 4 in flat space, it's just S squared plus T squared plus U squared. But in ADS space, because there's ADS radius, you have another dimension parameter, you can have a constant. Similarly, for the D6 R to the 4 in ADS space, you can 6 derivative, 4 derivative, and the constant. So this is ansatz by some knowledge about how this is effective action on ADS5 cross S5. Okay. Then of course, now I try to fix those unknown coefficients. And well, basically the information I have is 2 integrated correlator, order by order. Right? So in particular, is this at the supergravity level, I have 2 conditions to fix one number. So this is a good check. At the R to the 4 again, so I have 2 conditions fix one number again. So it's a good check what we did is correct. And at this order, D4 R to the 4, now you have 2 numbers with 2 conditions. I can fix them. In principle, I can also use a flat space limit because I know what it is in flat space. So in principle, I have 3 conditions if I want to include a flat space. That again give me another consistent check. Finally, for D6 R to the 4, well, 3 numbers, so I need the 3 conditions to fix it. All right, so that would be the answer if you do what I said, and that's the answer. And this is the answer as I emphasized in the large angle expansion for finite coupling. And now I put back the space-time dependence. Again, so until here, D4 R to the 4, if you take a flat space limit, it's a non-trivial check to compare the flat space. And for the D6 R to the 4, I use the flat space to fix those numbers. So that won't be a non-trivial check. Well, just to comment that this is a 4 point. If you're interested in higher point, actually, for a particular correlator, so-called maximally U1 violating correlator, you can start from here and start to recursively construct so-called maximal U1 violated. That's another story.
Sorry, can I just confirm something? So you don't have 2 loops. Normally would sit behind between the second and last line if we were in 10 dimensions, right?
Let me make sure. I think.
Where is 2 loops?
Right, you are. No, 2 loop is here. So this is D6 R to the 4. 2 loop is here.
Where is the 1 loop is C0? I see.
1 loop is C0. Yes. So those are numbers which I didn't really explain. Yeah, they are the numbers for the supergravity. They don't have tau dependence. Yeah.
And could you also match these numbers?
Yeah. So this one was done. 1 loop actually was did by Chester. Well, it was used to fix 1 loop result. So when people use unitality to construct 1 loop, because of UV divergence, well, it's not surprising that the number was not fixed. Then if you insist, that number is fixed by localization, you can use that to fix it.
Sorry, what UV? I thought it was finite. Why is it UV divergent?
1 loop in 10 dimension, it's a box integral. It's a UV divergent. And
maybe I'm saying something very basic, but I thought it canceled that 1 loop in supergravity, no? Because of supersymmetry, the divergence. No, isn't it finite at 1 loop? No.
No.
The box diverges starting in D equals 8.
Yeah.
And
the UV counter thing is R to the 4.
Okay, I think I'm missing something basic about the dimensions we are in. In 10D,
dimension.
In 10D, the box would be finite at 1 loop, right?
No, it's a divergent.
Divergent.
Yeah. Well, you have four
The box
propagators,
says
right?
It
You
has
have
8 powers of loop momentum in the denominator, 4 propagators. So if you have D8 or D10, it will diverge.
Okay. Yes, of course.
Yeah.
Okay.
And it's related to the fact that when people use a bootstrap to fix this object, there's there's an ambiguity they were not able to fix. Basically, it's related to the UV divergence. Right. Sorry. Sorry it takes so long. So let me just summarize what we did. Yeah. So we studied the integrated correlator. I think I focused on only one of them, but in principle, we know, well, it has to be heavily studied, 2 of them at least. In principle, there's a third one. Well, people believe, well, we believe you need a third one. Well, obviously you need a third one to fix these 3 numbers if you don't use a first space limit. But anyway, so we focus on one of them. This is basically the simplest one. And for this one, we were able to write a formula for arbitrary n and arbitrary coupling. And the formula make manifest the SL to Z imbalance of the n-forcible YAMUs. And that formula, we found that it obeys some interesting Laplace difference equation that relates to correlators for SUN and those for SUN plus 1 and SUN minus 1. Then I play a little bit with this conjecture formula. We studied loop expansion and try to compare with the known answer from a more standard method. And we studied, say, the Holder expansion or large lambda expansion. And finally, I also studied large N expansion for finite coupling. And for that, I even reconstruct the unintegrated correlator and compare with the string amplitudes. So as I emphasized, so this was a conjecture formula. Maybe you guys are more familiar with this kind of differential equation. It would be interesting to prove it. So either prove the formula or prove the differential equation. So the formula has this lattice sum, kind of suggesting, I don't know, I just made it up. So maybe there's 6-dimensional origin, you compactify in 2-dimensional lattice, and enforceable YAMUs has this 6-dimensional origin, maybe. The other question was obvious. There's another integrated correlator. For that, we have studied in large N expansion. As I show you the answer, in the large N expansion, not only you encounter so-called non-holomorphic Ison series, but you also encounter the generalized non-holomorphic Ison series. And the simple change of the name actually indicating the function is much more complicated, especially this contains so-called instant-on anti-instant-on pairs. Anyway, so it was clearly interesting to try to extend our study for this object and for finite n. Then there's a class of higher point correlator one could in principle to study. For those ones, the associate function is not a modular. Well, I haven't seen. So there's modular function. So those guys for 4 point, so-called modular function in the sense that they are invariant under SL2D. But for higher points, when you study so-called U1Y leading ones, then you will encounter modular forms. They transform, say, covalently under SL2D instead of invariant. And the whole talk, I have been only focused on the correlator of the lowest operator. Right? So it will be interesting, obviously, to study higher weights. And people found that there's an interesting relation between, well, in the larger N expansion and the strong coupling expansion, or namely the say, supergravity limit or some alpha pi expansion. People found there's some interesting relation between this lowest weight operator and those high weight ones. But the question, well, I don't know, probably not. But is there some? Is such a relation also, remains when you do small coupling expansion? I don't know. But of course, most importantly, probably that's why you asked me to talk here, is any connection with integrability. And I think this should end my talk. Thank you very much. And sorry for going on.
Thank you for your very interesting talk. And now we have time for questions.
Do we?
Can I ask a question about what happens in the large N limit when you take lambda to I pi? The reason I ask is because the perturbative radius of convergence that you're getting is, you know, or maybe it's minus pi squared.
Yeah.
Yeah. Anyway, there should be a singularity for unphysical coupling related to that. And like in other contexts, like the cusp anomalous dimension, it's the same radius of convergence, and we kind of know physically what's going on in terms of these flux tube representations where you have a rapidity representation, which is finite coupling slides. I wondered if you had any picture of what's happening there.
There's a
when you
branch
hit the radius of convergence.
So yeah, so this is divergent. I think if you said this is to like I pi
or minus pi squared,
yeah. So this pi. This integral divergent. I believe I checked it, but I don't have any explanation or so on. But it is divergent indeed, as I said.
Okay. Thanks.
Yeah, so we do have an integral explicitly. One can play with it if you want. Yeah.
And doesn't necessarily divergence should have like a branch cut, like the spectrum has branch cut there, and on any actually not only at I pi but on all integer I pi ends.
Yeah.
In the form of the unintegrated correlator, please.
Unintegrated, yeah. So,
the Malian one.
Yeah, this one.
Right, just 1 second. So you say that there is the Eisenstein 3/2. So so this, for example, this s squared plus t squared plus u squared minus 3. The minus 3 is not in flat space, right?
Yeah.
So somehow the effect of going from flat space to ADS is this minus 3, right?
Indeed.
And below this STU would be the flat space, and these other terms.
That's correct.
So can you understand this minus 3?
No. The simple answer is no. Yeah. Yeah. Well, I think Michael was saying. Well, roughly speaking, I have D4 out to the 4. Then I compactify on ADS 5 plus 5. There's a D4 can go S5 or go ADS 5. So basically, if we go S5, then you don't see the derivative, right? So this will
sorry. Can you repeat what is just said now?
Oh, I was saying. So this will be D4 out to the 4. Right in ADS 5 plus 5.
Yes.
And so if with the D, the derivative will go to S5, then so you know this bigger number. I don't see the derivative from ADS point of view, right? So if the derivative go to ADS 5, then I see this derivative.
So this could be related to what you were saying about this, considering different weights, right? To see the sphere better.
Yeah. So is there anything else to contribute D4? Yeah, probably just D4. Yeah. So, but this number, I don't know if there's a way to really compute it and see what I said.
I mean, because clearly, let me see if I understand. In flat space, there is a reason for liking this Eisenstein series, right? Because of S-duality. But if I did string theory in ADS and I take this to be the definition of a scattering amplitude in ADS as flat space plus a small correction, would I still be able to argue that these coefficients organized like this should have the same properties as in flat space? And...
Not necessarily. Just from simple modular invariance, I don't know. I could put the E3 half here. These two don't have, well, naively.
So the 3 could be E3 half, for example, right?
Yeah, exactly.
I see.
Not the obvious why it has to be like that, but probably that's the reason. But so in flat space, this result I didn't say. One way to derive it is just to understand the amplitudes, to understand how the supersymmetry constrains the amplitudes in flat space. But to do that, I cannot say too much detail, but it turns out you have to study 6-point amplitude to really to derive those results if we from amplitude point of view. And the difficulty is that if you try to mimic something like that, I have to study the 6-point correlator or Melling amplitude, and the supersymmetry constraint of such an object is not well known. So yeah. So in particular, this delta Q, we know very well, but the corresponding, the corresponding I at 6-point is not known. There's supposed to be some factor you can factor out, but in general, we don't know much. So we only know for the so-called maximally U1 violating guys, that's so-called IN. But to derive differential equation for those Ison series, you need not the maximal U1 violating. Actually, you need the non-U1 violating. In the amplitude case, we always have delta Q. We kind of know it. But yeah, for correlator, well, at least this was not in literature.
And if you go